I haven't done that for a while. A little bit of music for you to get started. This is a bit of a long video, so I guess I'm trying to appease the video gods. PowerPoint 15.1a, energy cycles, specifically the Born-Haber cycle. Accessing your prior knowledge, we need to remember first ionization energy. The enthalpy change for 1 mole of a gaseous element to lose electrons to form 1 mole of a positively charged gaseous ion. The gas actually, sorry about that. This is actually just a scan from your textbook, and I find it interesting that they say the electron is in the gaseous state. A lot of textbooks will not say that, a lot of formulas will not say that. But the sodium and the sodium ion are definitely in the gaseous state. Costs energy to make that happen. Electron affinity is when 1 mole of gaseous atoms gains an electron to form a mole of negatively charged gaseous ions. It is the enthalpy change associated with that. Typically it is exothermic unless it is the second electron affinity, which we'll encounter later in this process. I want to remind you about your data booklet. It does have first ionization energy data and electron affinity data in your data booklet. We will use it quite a bit today. The data booklet, not this table specifically. I want to remind you about the lattice structure for ionic compounds. We have what we might call a formula unit here. We do not use the word molecule because ionic compounds do not form molecules. Instead, we have this large three-dimensional structure with alternating negative chloride ions and positive sodium ions in the case of NaCl. Lattice, the idea of a lattice structure. We also need to remember Hess's law, which basically says if I'm going to make a series of reactions, it does not matter the path. A to C is the same energy change, so the delta H of A to C is equal to the energy change of A to B plus the delta H of B to C. Hess's law says it doesn't matter the path, the total energy changes are going to be the same, and we will utilize Hess's law today. The big idea, the concept of the energy change in a single step reaction being equivalent to the summation of smaller steps can be applied to changes involving ionic compounds. Today, the focus will be on lattice enthalpy. There are a couple of other terms within 15.1 that will come later. First of all, an understanding, this is a simple one. Representative equations can be used for enthalpy, energy of hydration, ionization, atomization, electron affinity, lattice, enthalpy, covalent bond, and solution. Let me give you an example. For ionization energy, I can use a representative equation. The metal in the gas form becomes the metal positive ion in the gas form plus that electron. This is a representative equation. Bond enthalpy, I can have something like Cl2. I'm just using X2 as a generic form, broken down into 2x. So obviously in terms of bond enthalpy, Cl2 becomes 2Cl. That would be an example. For ionization energy, we saw this earlier. We get the ion. So these are specific examples. We need to be familiar with this notation using equations to represent a process. Understandings here, quite a few that will tie together. Lattice enthalpy and the Born-Haber cycle are the focus of today. There are some terms like hydration enthalpies, which we will deal with later. So I'm not going to focus on all of those, but I did highlight some words in red here. If there are no words in red, it means the entire statement is appropriate for us. Construction of Born-Haber cycles for group 1 and group 2 oxides and chlorides. We'll do that together. So, first of all, let's define lattice enthalpy. It is the focus of our work today. It is the energy required to convert 1 mole of the solid compound into gaseous ions. And the solid compound we're referring to here is an ionic compound of some sort. So if I use the general equation, I've got some generic metal plus nonmetal solid, and I'm going to input energy. It's going to be an endothermic process to make the gaseous ions. Specifically for sodium chloride, I'm going to get the sodium and the chloride ions, or for sodium oxide, I'm going to get the sodium and the oxide ions. This is done based on stoichiometry. 2 sodiums here means I need two sodiums here. This is just in diagram form. Sodium chloride in solid form. I'm going to add heat and make the ions in gaseous form. This is, by nature, an endothermic process, as defined in this way. Now the Born-Haber cycle, this is actually from the textbook I used to use because I like the diagram better than the current textbook. There are many ways to teach this process. The method I'm going to use worked quite well the last few times I've used it, and so I'm modifying it a little bit, but I'm sticking with the main method. The main method is this. We're starting with elements in standard state, and if we form the solid ionic compound, that is the enthalpy of formation. So that's one process. Now, I can, because of Hess's law, I can go a different path. As long as I end up in the same place, I will get the same delta H. Alternatively, this path from elements in their standard state to gaseous ions, this path, I can go an alternate path. So there are lots of different ways to think about this. We need to break the process down into different steps, and that will be the focus of today. What are these steps so that we can make this energy cycle and solve for that lattice enthalpy? Because this value is really not able to be found directly through experimentation. Enthalpy of atomization is the first step we're going to focus on, and it is basically taking the metal and the nonmetal involved. This is a solid ionic compound, so we have a metal and a nonmetal. We need to make them atoms in the gaseous state. So I have the elements in their standard states, and I need to make them elements in the gaseous state, and that is enthalpies of atomization. So let's take a look. First, I need to turn sodium and chlorine into gaseous atoms, individual atoms. For sodium, this is simply the delta H of atomization. This process of going from a solid to a gas, for sodium, costs 107 kilojoules per mole. It is an endothermic process. Typically, this value will be given somewhere. It's not in the data booklet. For chlorine, it is actually the bond enthalpy. If I want to make 1 mole of chlorine atoms, I need to start with a half a mole of Cl2 molecules. So I know the value of the bond enthalpy for chlorine because it is in the data booklet. It's 242 kilojoules per mole. So if I need to break half of a mole of Cl2 molecules, the bonds here, to get 1 mole of Cl, it's going to be 121 kilojoules per mole. So these two steps are the atomization. I've turned sodium solid into sodium gas, and I've turned chlorine molecules into chlorine atoms. Just a reminder that the bond enthalpies are found in the data booklet in table 11. We can find the value for chlorine as 242. We had to divide that by 2 because we were only using half of a mole of chlorine gas. The next step is the electron affinity. I'm going to make the gaseous anion, and I'm going to have the metal atoms. I'm not going to mess with the metal atoms. So I'm going to take gaseous atoms and make them gaseous anions. That is the electron affinity, and this will take place for the negative ion, which in our case is chlorine. So chlorine needs to add an electron to become chloride. This value is found in the data booklet, and it is negative 349 kilojoules per mole. Back to the Born-Haber cycle. Next, I'm going to work with ionization energies. I'm going to take metal atoms to form cations. So this is the ionization energy for the metal ion. In the case of sodium, if I'm going to think about sodium chloride, sodium as a gas, it is already a gas because it has already gone through the delta H of atomization. It has gone through the process of atomization. So it is a gas. The amount of energy it costs to remove that electron is 496 kilojoules per mole. Again, this value can be found in the data booklet. It is 496 kilojoules per mole, just as stated. Now the next step in this overall process is lattice enthalpy. As written in this form, lattice enthalpy is an endothermic process to go from the solid compound to the gaseous ions. Here's a diagram. If I'm going to go from the solid compound to the gaseous ions, it will be endothermic. I can actually write the reverse reaction, which would be exothermic. We need to remember that it's not that the reaction is reversible, it's that I can reverse the reaction and change the value from negative to positive. For endothermic, it's going to be positive. Exothermic, it's going to be negative. The process will be negative. So let's take a look at this lattice enthalpy. I discussed already enthalpies of atomization, electron affinities, ionization energies. I didn't really discuss much enthalpy of formation. I can find this data in the data booklet or in other places for the enthalpy of formation, and that is the forming of the compound from its ions. So in this case, it's Na as a solid plus 1/2 Cl2 as a gas, forming NaCl as a solid. And I kind of glossed over this because it just seems a bit simplistic and it doesn't need as much definition or defining. But I think it's worth mentioning here. That process of enthalpy of formation we can define with an equation, and we can find the value for the enthalpy of formation of sodium chloride. This process starts with elements in their standard states and forms the solid compound. This process that I'm outlining here with the laser pointer, if you will, goes from elements in their standard states to the gaseous ions. Then I can talk about lattice enthalpy, which is the solid compound to the ions, or the ions to the solid compound. Now, what I need to do now is use Hess's law. Hess's law essentially says that the delta H of formation plus the lattice enthalpy is equal to the atomization plus the bond energy plus the electron affinity plus the ionization energy. So let's take a look here and see if we can make sense of this. This process is these two processes combined. It's the enthalpy of formation and the lattice enthalpy. This process is all of these combined. Enthalpy of atomization, bond enthalpy, electron affinity, and ionization energy. Hess's law says that if I combine these two values, which is these two values here on the triangle, those are equal to the combination of all of these values, because my starting point, elements in their standard state, and the finishing point, gaseous ions and cations, is the same. Hess's law says it doesn't matter what path I take. So I'm going to do some algebra and rearrange for lattice enthalpy. I have the delta H of atomization plus the bond energy plus the electron affinity plus the ionization energy minus the delta H of formation. So let's do a little bit of writing here. Let's put these values in. The delta H of atomization we found earlier was 107 kilojoules per mole, plus the bond energy, which we found to be 121 kilojoules per mole, plus the electron affinity, which we found to be negative 349 kilojoules per mole, plus the ionization energy. Ionization energy we found to be 496 kilojoules per mole, minus the delta H of formation for sodium chloride. The delta H of formation for sodium chloride is negative 411 kilojoules per mole. I think that value is either going to be in the data booklet for some compounds, or it will be given in order to find the lattice enthalpy. When I do the math for this process, I get a lattice enthalpy for sodium chloride to be 786 kilojoules per mole. That means it'll cost 786 kilojoules to separate a mole of solid ionic sodium chloride into the gaseous ions of that compound. So I want you to think about kind of the process we went through here. We're going to summarize it a little bit over the next few slides, but I want you to pause. This is the first time you've seen this process. It's going to take some time to kind of assimilate the understanding of the process. Don't consider yourself to be struggling if you don't understand it the first time through. It is common for students to take multiple attempts at understanding this, and I'm okay with that. I'm happy to help you through that process. Now, the lattice enthalpy can be found in the data booklet in table 18, and we can compare. We got 786. The data booklet says 790, so we're ballpark. We're really close. We're right there. In fact, to two significant figures, we are the same. So this is a good thing. This is a diagram from your textbook that gives us an outline of the process from a slightly different perspective. It just kind of labels the steps: atomization for the sodium, bond energy for the chlorine, ionization energy for the sodium, electron affinity for the chlorine, and how can you relate that to the lattice enthalpy. The one thing I didn't like about this particular diagram is it leaves off the delta H of formation for the compound, which is why I really like the triangle that I prefer to use. Although again, I'm gonna remind you that you can find other methods out there that describe this process, but I really like the triangle because it keeps the path in my brain. It keeps it clear. This is an enthalpy diagram of the process, again from your book. We're starting with the elements in standard state. I'm going to form sodium. I'm going to take sodium, so let's figure out each step. Sodium solid to sodium gas. Chlorine molecules to chlorine gas as elemental particles, atomic particles. The next step is the ionization energy of the sodium. The next step is the electron affinity of the chlorine. And the last step is really that lattice enthalpy, the overall step of going from the solid sodium chloride to the gaseous ions. And what this does not have, that I talked about a little bit earlier, and I'll talk about it now, the last step that it does have, is the delta H of formation, which is going from the elements in their standard state to, I wrote there when I wanted to use my laser pointer. Delta H of formation is going from the elements in their standard state to the solid ionic compound. This is a different representation than what I use. Again, I use this triangle where here I have the elements, here I have the ions, and here I have the compound. I have to kind of remember some steps along the way, like to go from elements to ions involves atomization and so on. So it does require me to remember some steps. I find that this diagram works for me. So I'm sharing it with you. Sharing is caring. So this is just a reminder about Hess's law, which we kind of have utilized here and talked about. I just want to maybe briefly remind you of this. If I call this delta H1, this is delta H2, and this is delta H3. Delta H1 is all of these things combined. The atomization, the bond enthalpy, the electron affinity, and the ionization energy all combined. Delta H2 is the delta H of formation, which is this step. Delta H3 is the lattice enthalpy, which is this step. So all of these combined is equal to these two things combined. I've already given you some background on where to find this data, but I did want to have a slide to kind of summarize that. The bond energies for the non-metals are going to be found in the data booklet, typically, table 11. The enthalpy of atomization for the metal is usually going to be given in the problem. It might be what you're calculating. If you're given everything else, you can calculate that. The electron affinity is in the data booklet. The first ionization energy is in the data booklet. And in cases where we need the second ionization energy, like for magnesium, we certainly can find the second ionization energy as well. Enthalpies of formation sometimes are available in table 12, sometimes they're given. And the lattice enthalpy is usually what you're solving for, but not always. Sometimes you're given the lattice enthalpy and you're solving for some other step using Hess's law. Lastly, in terms of applications and skills, quick reminder before I move into this next slide. I'm not going to just assume after one example that you've got this process down. This is one where I will be spending a little bit of time in class, lecturing, if you will, for lack of a better word, to give you another example. And then we'll do some practice problems. We'll have some discussion. All right. Applications and skills relate the size and charge of ions to lattice and hydration enthalpies. Our focus today is on lattice enthalpies. So, two factors, the size of the ion and the charge on the ion. I want you to look at this table. This is the alkali metal halides, fluorine, chlorine, bromine, and iodine. There are 20 different compounds here. I want you to see if you can find a pattern for how the size of the ion affects the lattice enthalpy. See if you can formulate a hypothesis and an explanation for this trend. Identify the trend and form an explanation. I'm not going to talk about it in the video. We're going to talk about it in class. And also, I'd like you to use the rest of the table. So the previous slide had just the top portion of table 18. Now we have all of the table. How does charge on an ion influence the lattice enthalpy? That's what I'm interested in you kind of working through now. And select some data from the table to identify the trend, form an explanation. We'll talk about it in class. In terms of international mindedness, the importance of being able to obtain measurements of something which cannot be measured directly is significant everywhere. It is used to find borehole temperature, snow cover depth, glacier recession, rates of evaporation and precipitation cycle, some of the indirect indicators of global warming. Why is it important for countries to collaborate to combat global problems like global warming? Something to contemplate. In terms of the nature of science, making quantitative measurements with replicates to assume reliability. That's kind of a standard nature of science practice. And then also energy cycles allow for the calculation of values that cannot be determined directly, such as lattice enthalpy. Connections to other topics, we need stoichiometric relationships to understand whether we're going to use half of the bond enthalpy or all of the bond enthalpy, those kind of things. Atomic structure and ionization energy, electron affinity, the atomic and ionic radii trends, bond enthalpy trends, periodic trends. These are all kind of things that relate to this topic. It really does have kind of far-reaching implications for our studies. In terms of a summary, I did my best. I always encourage you to come up with your own summary. Lattice enthalpy is the energy required to form gaseous ions from a solid compound. That's summary statement number 1. Summary statement number 2, the value for the lattice enthalpy can be calculated using an energy cycle called the Born-Haber cycle. And then lastly, there are 2 main factors that affect the lattice enthalpy of a compound, and these are the size of the ions and the charge of the ions. Once we've had our discussion, we can add some depth to this summary statement, but for now, we'll leave it at that. Thank you for listening. There are no checkpoint questions for today. We'll handle that in class. Certainly, if you have questions that can help guide our discussion, feel free to put them into the Google form, but trust that we will actually be spending some formal time going over this process in class together. Thanks again. See you in class.